Hi, my name is Ashley Arcidiacono, and I'm a recent graduate of the Hansen Lab at Florida State University. And today I'm excited to share with you one of our newest publications in the Journal of Materials Chemistry A, titled Structural Insights to Metal Ion-Linked Multilayers on Metal Oxide Surfaces via Energy Transfer and Polarized ATR Measurements. We're joined on this paper by Professor Igor Alabugan from Florida State University and Scott Saavedra from the University of Arizona. Metal ion-linked multilayers offer a means of controlling interfacial energy and electron transfer for a variety of applications that range from solar energy conversion to catalysis to sensing and beyond. Despite the importance of structure in these interlayer energy transfer processes, there's very little known about the distance and the orientations between the molecules in these ion-linked architectures. Here, our goal was to gain structural insights into these assemblies, and we did this via the growth and study of a series of multilayers that consist of an anthracene FRET donor that's ion-linked to a series of asymmetric porphyrin FRET acceptors. We were then able to use the relationships between FRET efficiency and donor acceptor relative orientation that are shown on the slide here to gain information about molecular orientation in these assemblies. The first step in doing this was to confirm the growth of our ion-linked bilayer structure. We did this through the use of UV visible absorption spectroscopy, where the additive absorption spectra is indicative of the ion-linked bilayer structure. We then used time-correlated single photon counting in an attempt to monitor the anthracene to porphyrin energy transfer by determining the difference between the inverse lifetimes of anthracene in the bilayer and then anthracene in the absence of that FRET acceptor porphyrin. However, we're only able to calculate a low-end estimate of the FRET rate in this experiment, given the time resolution. To circumvent these timing limitations, we performed ultrafast transient absorption spectroscopy, shown here. Briefly, TA spectra of the bilayer indicate FRET upon preferential, albeit not exclusive, excitation of anthracene, as can be seen in the full spectra, where anthracene and porphyrin character exist in all excited samples. Then, by monitoring the kinetics at 460 nanometers, we're able to determine FRET rates where the rate of FRET increases going from P3 to P2, and then the FRET rate is similar between P1 and P2. The difference in K-FRET between the bilayers consisting of P1 and P2 is smaller than one might expect for the typical R to the 6th distance dependence in FRET. And this observation indicated to us that perhaps the distance is not the only FRET relevant parameter that is changing between these two samples, and there could be an orientational difference that is contributing to these efficiency differences. Spectroscopic measurements like those that we've just seen, as well as light harvesting applications for molecule metal oxide interfaces, typically rely on mesoporous fused nanoparticle substrates, mostly due to their high surface areas that enable increased absorption cross-section. However, a majority of techniques used to determine the structure of molecule metal oxide interfaces, including the ones that we will show later in this presentation, are performed on planar substrates. So here what we did is we used, once again, time-correlated single photon counting to try to determine if there's a difference between the FRET rate between anthracene and our third porphyrin on mesoporous and planar substrates. And overall, what we were able to observe is that given that each sample and each film has the same solvent, meaning the same refractive index, and the same chromophore pair indicating a constant spectral overlap and donor quantum yield, we determine that the lifetimes are all similar between both planar and mesoporous samples, regardless of the nature of the underlying substrate. So this data strongly suggests that the structure of the bilayer film is similar on both planar and mesoporous substrates. We then go on to determine the orientation of our molecules relative to surface normal using polarized attenuated total reflectance. And indeed, we confirmed the suspicions that we had based off of our femtosecond transient absorption data, which is that as we change the identity of our porphyrin, we are not just changing the distance between our donor and acceptor, but indeed seem to be changing the orientation of that second layer porphyrin. As I said previously, polarized ATR only provides information about the orientation of the porphyrin plane relative to the surface normal. So to explore possible structures, we perform geometric calculations where the key structural parameters are shown here, where vector representations for anthracene and then our porphyrins are shown in red for anthracene and purple for our porphyrins. We found that in the case of our shortest porphyrin, P1, the short donor-acceptor separation leads to a high theoretical efficiency of FRET greater than 99% across a majority of the surface. In contrast, a larger variation is observed for the bilayer containing P3 that is shown here. There's an apparent radial band across the sphere that indicates those structures that exhibit stronger agreement between the theoretical calculated FRET efficiency and the experimental. So among the possible geometries, we show here the best theoretical experimental agreement. Overall, there are still a host of questions that have yet to be answered, but we are able to provide new structural insights into multilayer films on both planar and mesoporous substrates. And we are also able to demonstrate that polarized ATR and FRET can serve as complementary techniques to determine structure and orientation. Overall, the remaining questions in these studies remain, such as what role does the local environment and loading condition play, like the solvent or the metal oxide or the counter ion of the linking ion? What role do these play in dictating multilayer structure? And then also, given the energy efficiency that we are seeing here, can we design multi-layers specifically to enhance or suppress these energy transfer and electron transfers at will? If you're interested in reading this paper, you can find the DOI at the bottom of this slide.